Hello scholars and welcome back to Mr. Sniffin's geometry class. Wanted to talk today about the importance of vocabulary in geometry and not just like defining terms, but kind of how we can look at language as a means of creating math as well as how math creates language as well too. Let's look at it this way. We can use vocabulary to kind of draw meaning when we intend to converse or describe things. But having vocabulary unto itself has some form of utility, a usefulness, if you will. Like vocabulary provides us this intent, or the ability to show intent, or the ability to give directions when we're trying to add value to statements. Like when we want to describe things, we can articulate our ability beyond just kind of portraying it as a set of shapes, squiggly lines that add up to a person. We can describe all the different attributes of that person. The more vocabulary words we have provides us a sense of linguistic tools. We have a vocabulary tool belt that we can use to kind of look at everything around us, which is what we call verbiage. Verbiage is like your numismatic amount of words that you can describe towards something, a plethora, if you will, or some like grandiose collection bag of words. The more words that we have to describe something, the easier it would be for us to relate to a person, or have them relate to what we intend to prescribe to them. For me, I like to have a complex verbiage, a large verbiage, because I feel like it gives me this ability to kind of paint a scenario or paint a situation in a way that I want to draw out emotion. I try to use a set of words oftentimes to focus in on something, but when you want to add some flowery sense to your story that you're telling your friends, you want to, pick some words that draw out some emotion to them. Language itself has this interesting thing where it's not necessarily black or white. It's when we describe something, there's a sense of relatability. The way one person picks up on something is not exactly how you intend to mean it. There's like a gray area, if you will. Language is not as easy as like a 1 and a 0. It's not as easy as what we've been trying to focus on recently is this idea of binomial reasoning, like a yes or a no statement, like generating that flow chart of decision making. But there's a beauty in language in that way. There's like nuance in personal meaning. For anyone that's ever grown up in a multi-generational home, you might have a brother and sister, but parents, aunts, uncles, things like that. You can see how words have relative meaning. Your way to relate to just a simple current event or musician has some type of separate value than the other people in your home, particularly on this generational scale. It's why we have this concept of generations in the first place. You might choose different words. You might also use things, you might articulate kind of the pronunciation of different portions of the word, particularly if you grew up in a home where you have bilingual parents or you're bilingual yourself. The way that you might relate just to myself, just speaking like normative English, is going to be different as well too. There's this really interesting guy named Noam Chomsky who's like the grandfather of linguistics. He's like the Euclid, essentially, of contemporary linguistics. He describes this way in which we look at the world through this concept of what he called externalized language and internalized language. What he described as grammar, kind of the rules and the way other people force you to talk, as this type of external language. But the way that you yourself kind of interpret the world comes through this internalized process. We might use some of the same words to describe something, but in actuality, what we're looking at is a relatability to that sound that comes out of your mouth, right? Grammar, which is our internal language, is kind of like this linguistic hardware, if you will, for our meat machines. It's what gets generated in a way. How we interpret reality and interpret external language has that reflection in it. But I bring this up in contrast. You might be thinking like where we're talking about linguistics, like how does this relate to geometry? Um, and I think it's interesting. We have the ability to kind of describe large systems for people, but we also have them for math as well. There's a point where these things eventually meet. And just follow me here for a second. Um, Collectively, everyone's thought process is different, right? The language, how we express it, the vocabulary in our head, how it gets all interpreted varies, right? There's no one singular system of thought unless you were to describe all the variables that humans have, and each individual, your aunt, uncle, cousins, teachers, things like that. Maybe if we quantified everyone's system of thought, then we can say the holistic system has all these other delineated paths, if you will. And that's kind of the flavor, or the floweriness of biology. It brings about kind of variation. But even within people, we can look and reduce backwards, right? We presumably all have eyes or an ability to see, or theoretically we can describe humans as having kind of this genetic lineage of a particular form of eyesight. Brains get adapted in certain ways, joints are designed probably within, the same function, really. We're all kind of made up of all the same exact stuff, right? Brains function on chemical processes, so they have this other form of reduction associated with them. When you eat a bacon, egg, and cheese in the morning, it goes about and creates a new kind of you. There's a new flavor there. There's a new chemical makeup running on the software level. There's science that demonstrate we reduce another level. There's science that demonstrates how chemicals themselves function. Your bacon, egg, and cheese has carbohydrates, and in chemistry class and biology class, we learn about how nutrition influences the body. But there's also factors that go into the carbohydrate. There's components that make up that compound of water. We can reduce again. We call those our elements, or elements that get blown apart at kind of the foundation of the universe, at our Big Bang, if you will, most likely. But the chemicals themselves, whether they be the compounds or the elements, they can be reduced down into things like protons, neutrons, and electrons. Even further so, we can have science, or the field of physics, that describes the positionality of those things, or possibly even other forms of submatter that make up electrons and protons and neutrons, going even smaller, if you will. But in all of human history and all of what we understand, we can think about the most finite amount of whatever we can describe as. It all seems complex, right? But at a certain point, we can reduce down to a yes or a no statement. The most basic thing that's mathematicians call this zero. Sorry, call this a point. A point is essentially, or what some have argued, or most mathematicians argue, the representation of something which is zero-dimensional. Zero-dimensional in that it has no up and down, it has no left and right, it has no depth through it either, our third dimension. A zero-dimensional figure is but a place. It's a coordinate, if you will. It's just a fact, and it's not necessarily an actual tangible thing. And it's kind of a fascinating concept. If we can reduce our language down and our experience down to something which is incredibly finite, starting with a yes or a no statement, like a point, we can then go ahead and build up other systems from there. And that's basically our field of geometry. We start at what people call the most basic of measurements, the most basic of things, a point, and we can describe everything else around it as either not being that point or being that point. It exists at this, say, longitude and latitude, this scale, or it doesn't. But we don't describe the point necessarily as a thing, because once you are a thing, you can be touched, right? You have, presumably in the three-dimensional world, you have like mass to you. We don't describe a point as even that. It's just a finite measurement. Points give us this incredible ability to what we call dimensional reasoning. It's what I've been trying to touch on last week. The ability to use time, the ability to position people in places of history has value to it, right? The zero-dimensional figure allows us to basically tell if something is or isn't a yes or a no statement, but from there we also have the ability to create other shapes, or we can start to make shapes. So let's look at it this way. Points give us this ability to create dimensional reasoning, and a dimensional reasoning which is concrete. Let's take, for example, this scenario. If we were to have two different points, say, 2 different points in the sand, 2 different points or wherever. If we wanted to task a group of people with drawing or connecting these 2 different segments, theoretically we could say that there's a multitude of ways to connect these 2 endpoints. As long as we drew some type of silly straw-like line or maximized it and made it as straight as possible, we have an ability to fulfill our objective. Our objective or our task is really, really vague. It just only has, did you connect the 2 endpoints, yes or no? However, in geometry, we have this other question that we start with asking off at first. The other idea would be, if we have 2 points, what is the shortest distance, or theoretically the most efficient way to connect these 2 spots here? If I want to use the least amount of graphite, say that I want to have the most direct swing here, I'm going to go in my straight line. I'm going to connect these 2 points here with a nice flat straight line. And this is what we describe as a segment. It's the most efficient means of connecting 2 points. It's a direct line or direct connection in between 2 points. This is when we break out from this zero-dimensional concept into our first dimension. Our line here allows us, our segment here allows us to create our first new level of hierarchical thinking. Allows us to go to another set of instructions, if you will. Once we have this first level, we can begin to branch out. We have the opportunity to create more of these binomial reasons, these yes or no's. Almost like, if you will, and this is the cool way I like to imagine stuff sometimes, is with like decision-making trees we've all seen so many times. Once you get to one question and you do your yes or no, you have different outcomes, right? All branching out in all these various directions. Sometimes you can see these graphs drawn neatly, unlike my ability to do so, but you can kind of see the point. We get all these different cool things that we can make decisions on. And this is where we start to create new rules within geometry. So there's our point is our zero-dimensional figure. We start to expand out from there and we get our segment. But here's also how we go about describing one dimensions as well too. Take, for example, this figure here. This figure we're going to call a ray. It has one endpoint and it goes out into infinity. Our point represents that dot. Our arrow on the end is indication of a direction into infinity. We're talking that nice cool 0, 0 symbol. And with array, we get to begin to play with this notion of infinite possibilities. It no longer has a spot where it's going to stop at an endpoint. We have the ability to continue on throughout our timeline, throughout our decision-making hierarchy tree, into a multitude of other potentials. But we do, at least at this point, have some type of rules. We're not zero-dimensional, we're currently one-dimensional, and we're going to extend for infinity into the right side of the page. The next way that we can describe our next layer that we would have here is if we take that ray and basically draw that line going out in both directions. A line is something that extends from one point into infinity, as opposed to, like say, a number line where we go from 0 to 1. We can now kind of express this idea as having negative numbers, right? We can go on to -10, we can go to -20, and so on and so forth. Having lines, having rays allows us to create more and more complex scenarios, but we're wrapped in this one dimension. The way that we differentiate this between our second dimension is when we draw that secondary line, that y-axis that we normally would in our graphs, where we have our x going left, only left and right, our negative x or positive x, and our second dimension is now when we add another method of numerically counting it. That's not that same original left and right value. If it's not exactly left, if it's slightly up, it has a second dimension. If it's slightly down, it has that negative concept. This is why in our distance formula, we try to find exactly how far we're moving over, left or right, plus how far we're moving up and down as well. All of these decisions end up resulting in different methodologies that we can use, or kind of different structures we can play around with. This week, we're going to be talking about how we create the actual innate structures that make up geometry. We've mentioned already our formulas in terms of using our graphical sense, but how do the rules themselves come about? What I'd like to do right now is just show you a couple almost rudimentary things that we can do that generate sets of rules, and then I want you to answer a question at the end as well. That question I think is simple, but it's imaginative. But just look. If we were to take two rays, two lines, two segments, say, and just went ahead and crossed them, just nice long rays, and we can imagine this being in any direction. I just made an arbitrary method there. We can also do it with very tightly crossing lines as well too. But if we take two lines and cross them, we end up creating new systems. There's new hierarchies that automatically get formed by these simple characteristics of segments or lines crossing. Not waves, but nice and straight between those theoretical 2 points, if you will. Once these lines end up crossing, we get this thing called a vertical angle, which is when the angles opposite a vertex, or these crossed vertex, every single time they end up being congruent, no matter what. There's no way to disprove this postulate, this axiom. No matter what, when we cross these things, they end up always being congruent in terms of their angle, or what we said earlier last week, like their slope. And this is pretty interesting. This is just me drawing on a piece of paper. I didn't have to do my lines in a certain way. It just came about in a natural way. As we finish up here today, I want you to think about a particular question. These rules that I just demonstrated, at least for this example of vertical angles. When mathematicians from our various historical backgrounds came about and found these pieces of information to be true, was it something in which they discovered on one hand, or on the other, was it something in which they invented? Invented being like, did they create these things, or was it something to just be found? What I'd like for you to do is check out Google Classroom today. There's a little page for you to answer that question on, but you tell me. There's not necessarily an answer here. There's a lot of super genius mathematicians who have argued it in both ways. Let me know. Give me your opinion. I'll let you know mine tomorrow. If you do have questions, of course, drop by office hours and we can pontificate, if you will, and expand on our verbiage and try and find an answer for this. But until next time, stay safe and wear a mask. Bye.